Okay, so we're recording. First thing I need to tell everybody, first thing, welcome to Math219. First thing after that, then I need to tell everybody is you are being recorded, audio only, and what's on the screen. Okay, so you don't have to be, physically self-conscious, but just be aware, be advised for legal purposes that if you ask a question, the mic might pick it up somewhat. It is a heavily, location-dependent microphone, and so I don't really think it's going to pick up. I don't think it's going to record you enough that you'll be identifiable, right? But nevertheless, I might as well tell you. So let's see here. I want to remind y'all of some of these items from the recording that y'all all watched, I hope, except for one student who I know just joined the class. No problem. But the rest of you have watched this introductory recording. And so the class website, let me just remind you, here it is. And there's everything that you need to know about the class, all of the organizational stuff, and my lecture notes, copies that you might want to have. What's going to be covered in the course is here on the content syllabus. When is the exam? What are we planning to do next Tuesday? It's going to be on here, etc. So all of that is covered, of course, on that recording. So make sure that you understand all of that, sort of the logistics and stuff like that. Then over here in the second column, how to do well in the course. Also important, right? In a different way. And this is largely advice, right? But I think it's all good advice. This is advice that's based on, my let's say, I could say decades, but let me just say years. It doesn't feel as bad, right? Of experience teaching multivariable calculus at Duke. Anyway, I think this is all good stuff, and I hope you'll take advantage of that as well. By the way, while we're here, I'll point out the office hours list here is coming along. Right. There are still there's one remaining unknown in terms of that teaching assistant. So Michael Lee is one of the teaching assistants. Kai Shu, the location has not yet been determined, but we'll get that all straightened out as soon as we can. But while we're here, I'll also point out that today being Wednesday, note that 2 to 3 o'clock this afternoon, in other words, pretty much right after class, I have office hours. So if you have any questions from the lecture that maybe wouldn't have made sense to actually ask during lecture, that you want to get straightened out, office hours is a great time for that. You just come in. Everybody who's in office hours also has questions, right? Or perhaps is coming specifically so that they can hear what questions other students ask because they want to hear the answers, right? So anyway, it's a much more sort of, relaxed, kind of, comfortable place to ask questions. So anyway, right after class, I hope you all find that useful. Okay, let's see here. So, a couple of real quick things. I've already said this on the recording, but do make sure to read through the whole webpage. There's a lot of stuff on. It's a lot of stuff on there. It's a lot to read, I know, right? But it's all very important stuff, and make sure you get all that. And then I'm also going to remind you about the biggest point of all is what this course is about, fundamentally, philosophically, you might say, it's about ideas, right? So very, very many students have had math classes where the focus was on whether you do or don't get the right answer at the bottom of the page. And if you do, full credit. If you don't, that's too bad. And that's not what math should be about. Math is about ideas, just like history, frankly. I think the analogy is a lot stronger than a lot of people realize. If you took a history class that was all about, you just need to memorize the dates and the names, and that's it, right? That'd be a terrible history class. So likewise in math. And of course I expounded at length on all that in the recording. And then let's see here. I also wanted to come over to back to the web page, and I just want to make sure everybody clicks on this link right here, course grades. Right? So this is another ultra important thing. Ultimately, we're going to be doing what's called a weighted average. of your grades on the various graded items, where these are the graded items and their weights, and then we basically infer your course grade from that. So if you're not entirely sure that you understand what that means, come talk to me, right? This is a perfect topic for office hours, by the way, right? But I want to make sure everybody is unambiguously, right, down to the detail, clear on how course grades are going to work. So anyway, make sure that you read all this. I ultimately, once you understand it, I think the formula for your course grade is actually quite simple. There is, of course, a process to getting to understand it, and perfectly happy to discuss to help you get there. Okay, I think that may be all I was going to say here. Of course, there's a million other things that y'all can watch on the recording. But does anybody have any other questions about any of it? Yeah, question.
I was looking at the weighting of everything for our grades, and it kind of seems that we don't have a final.
It kind of seems so, because we in fact do not have a final. That's right. That's an experiment that I'm running this term. The main motivation there is just that this class is so compressed, it's so compacted, right? And even in a semester, an exam that happens at the very end of the semester, from then to the final exam, sometimes as little as 5 or 6 days. It's quick, right? In the summer, that's 2 days. This is preposterous, right? And so it just doesn't seem, a different point of view that one could take is to have a final but not a third midterm exam, right? So anyway, I've done it that way for a long time. This will be my first time non-COVID semester to try this way. So, but you're right, no final exam. Yeah.
In DUCA,
yep,
there is a final exam time listed.
Oh, yes. They put that in there so that instructors have the option, and at some point they'll probably ask me, if I'm actually going to be giving a final, and I'll say no, and that'll either disappear, or if it doesn't, don't worry about it. You have my word right now, I'm not going to be there. There will be no final to take, so just ignore all that. Yeah, good question. Anybody else? Everybody's happy? Good deal. Okay, so that's logistics. Now let's get into some actual content, and this is arguably kind of a precursor to the actual course content. But I do think this is a nice segue into doing some math. I want to try to talk about why multivariable calculus is important. I think everyone should have a good answer to this question. You may be wondering, why am I here aside from my major requires it, right? So why does your major require it? So, okay, I hope this is an easy pitch. Single variable calculus is important, right? In fact, arguably the name itself, calculus, is kind of the dead giveaway there. The word calculus, if you trace it back to its roots, roughly means computational tool, right? And so there are different, out there in the math world, there are different computational tools that are sometimes referred to as a calculus, right? But this one is the calculus, right? So that, again, just the position it has in the language screams how unbelievably important calculus is. Okay, so what is calculus about? Well, calculus is about derivatives and integrals. Again, broad brush strokes. So what is a derivative? Derivatives are a tool for understanding how things change. Now, how's that for a broadly applicable power, right? Stuff that changes. My God, everything in the world changes, right? Well, calculus is how we understand and keep track of all of that. So, wow, that's a lot. Okay. So what's an integral? Well, different ways to say it. I like to think of integrals as a tool for computing what I call accumulating quantities. Stuff that you can chop up into pieces, and the whole is the sum of the parts. call them accumulating quantities. We're actually going to spend a bunch of time in this class talking about specific, possibly less intuitive, possibly even counterintuitive accumulating quantities. But that's for much later, by which I mean in about a month. Right, summer pace being as fast as it is. But anyway, so my gosh, accumulating quantities, whole is the sum of the parts. Again, the world is full of such things. Right, so I think this is an easy pitch that single variable calculus is important. Okay, well, roughly speaking, multivariable calculus is just all this kind of the same ideas, just in a multivariable. For example, the world that we live in is a 3-dimensional world, not a 1-dimensional world. Right? That'd be a boring world to live in. In a 3-dimensional world, if you want to understand how stuff changes or how stuff accumulates, you're doing it in a 3-dimensional sense, not a 1-dimensional sense. And so, just as some explicit examples, if you want to talk about how temperature changes over time, well, if you knew big T as a function of little t, that would be a single variable calculus problem, right? But if big T, right, is a function of position, right? So you could imagine if you're over here in 3 space. Well, here we are in 3 space, right? And so let's see here: x-axis, y-axis, z-axis, for example, right? Then everywhere in this room is a location with 3 coordinates, x, y, z, and at every point in this room there is a temperature. So temperature is a function of 3 variables. How would I take its derivative with respect to time? Right, so it's a function of 3 variables, none of which are time. All of the input variables are changing. Right, if you imagine that you are moving with some velocity, as indicated by some vector, x, y, and z are all changing. Which derivative do we look at? Or if somehow all of them, how do we combine them? Do we add them up? But there's big questions here. Is what are the detail doubles that recognize how we're going to generalize the idea of a derivative to a multivariable setting? Is everybody on board with the okay, that's different aspect of this? Yeah. Okay. Alrighty. Okay, and then let's talk about accumulating quantities. An old formula that y'all all know is that mass is density times volume, right? Old news. High school physical science class, or whatever they call it these days. Okay, well, what if the density varies with position? So maybe, for example, I've got a thing here, and maybe it's not very dense over on the left side, but over here on the right side, and the further you go to the right, the more dense it becomes, and it just gets denser and denser and denser the further you go to the right, and maybe at some sort of an angle, something like that. How are we going to compute the total mass of this? Well, I can't multiply volume times density because density is not constant over the volume. So now integrals, single variable integrals would tell us, okay, we'll take some sort of slices, right? And then on each slice, maybe you multiply density times volume. Well, the density is not constant on the slices either. So we're going to a pretty nasty problem here, right? This is a multivariable version of a problem that y'all have seen in high school context before, or in a calculus context before. But this is still a new thing, and we're going to have to figure out how to make sense out of it. Okay. All right. Now, for some field-specific examples, right? These examples up here seem kind of, fundamental or basic or arguably boring. But let's talk about something, field-specific examples. So now I'm going to start with an econ example just because why not? But a lot of people think of calculus as being a tool for the physical sciences, and that's just not exclusively the case. Economics makes tons of use of calculus. And so do some of the other social sciences. Sorry, I forgot to click the ringer off on my phone. Okay, how do economists make models? Well, it's all different. It's all I don't want to overgeneralize. But here is a great big equation that could be an economic model. And notice in this equation, it doesn't explicitly say P equals or, L equals, right? It's just that, well, you got all these various quantities that all together, in this sense, they combine in this certain way, that expression's got to be 0. So if I want to know, for example, how does P change with time? Well, I would have to solve for P. I can't solve for P. Look, P is inside of not only a cubic, but it's also in an exponential. This is a transcendental equation in P. You cannot solve for it, right? Also, in order to know how P changes with time, I would need to know how all of the other variables change with time. So how are all of these other variables' rates of change going to factor in to figuring out what P's rate of change is? And well, this is a complicated question. This is a subject that we're going to talk about, not the economics of it all, of course, but the just how to take an equation and use some rates of change to infer other rates of change. This is something that we're going to talk about in this course, and very, very important in economics. Any econ majors out there, by the way? No? All right. Well, you're going to learn some anyway. And by the way, I like to interject just as a philosophical point. Even if the applications that we spend a little time on in this class aren't what your major is, good. Broad liberal arts education, right? And it's important to be exposed to things not because you need them, right, but because you're here to learn about more than just, this is not vocational school, right? So it's a good thing to be exposed to, again, topics that you don't necessarily immediately need. Okay, I'm also going to point out, I think this is a big one. Check it out. There are 5 different variables in this equation. Arguably 6, depending on how you want to count, because we're taking derivatives with respect to a variable as well, namely time. So depending on how you count, this is either 5 or 6 dimensional math, which is pretty scary if you think about it, right? So a lot of people make the mistake of thinking, oh, well, the purpose of multivariable math is that we live in a 3-dimensional world. I made that point myself, right? And because 3 is bigger than 1, that's why we need multivariable calculus. Wrong. That is one of many reasons that we need multivariable calculus. The physical world is not, the only variables that we're going to be interested in. Location is not the only thing we want to keep track of. Yes, location is 3-dimensional. Fine. Right? But something as concrete and applied and practical as economics needs apparently 6-dimensional math. Yeah.
Is that a real equation? Or
No, I made it up. Nah, this is just a for example. Yeah. I just wanted some stuff to. I wanted specifically an equation where solving explicitly for the variables was just not a reasonable thing to be able to do. Yeah, so I made something deliberately ugly. Right. Okay. Anybody else? All right. Now, good news. While when we're doing math in 3 dimensions, which will be most of the course, to be fair, when we're doing math in 3 dimensions, it is very useful to visualize what that looks like and what kind of a shape am I on, and how do I draw that, and how do I visualize it? Think about it geometrically. True. When we are doing 6-dimensional math, You don't have to, nor can you visualize or certainly draw what it looks like, right? It's just not realistic. We're intrinsically three-dimensional critters. Our paper is two-dimensional. And at best, we can pretend to draw three-dimensionally, right? And you look at these pictures here. I'm pretending that I've drawn a three-dimensional picture, but nope, it's two-dimensional, right? And so it's at best we can play like we are doing three-dimensional geometry. So don't worry about visualizing in 6 dimensions. It's not going to come up, and you're not going to succeed if you try. And so don't. All right. Okay, now here's some scary-looking equations. These are called Maxwell's equations. They're huge in physics and engineering, and a little bit of chemistry, arguably. But anyway, certainly in physics and engineering. So, wow, that's horrifying, right? So, reasonable questions. What does all of this mean? Well, this is all multivariable calculus objects. Everything. Well, there's some physics in there too, right? But the items in play here are all modeled by objects of multivariable calculus. So when we study multivariable calculus, we're going to be studying all of the tools really that are necessary to understand some tremendously sophisticated physics. So what do these things mean? What's that thing? What is that? We're going to learn that. What is this thing here, a ds vector? That's scary looking. That's something that we're going to also eventually learn about. But I want to point out that we will further be asking. Okay, but it's not enough to simply know what these things are that are in this equation, but we want to understand how can I best understand what this equation itself is saying. Right? Understanding the objects is not the same as understanding the meaning. Right? Okay. And then how does this help us understand physics? Right? How can I better understand electric fields and magnetic fields? More so electric fields in this class, but as a result of what we're learning here. So this is going to be a big object of state. We're not going to do, again, this is not a physics class, so I'm not going to really focus on the physics of it all. But as it turns out, I'm going to try to keep this short because this is a bit of a digression, but as it turns out, not only is math a great tool for understanding physics, turns out that the physical universe is just a fantastic model for mathematical ideas that we need to understand. So physics is going to help us understand math as well. And that's my motivation for all the physics that we're going to be doing. Okay. All right. Okay, last one, and this is a genuinely scary equation. Might not look it, but this is far worse than Maxwell's equations. If you are in chemistry or physics, really big deal. And just as a for example, if you want to understand how is it that atoms are held together in molecules, right? How does that work, right? In high school physical science class, they told me that there's a bond, and they drew a little picture like there was a little rod connecting one little billiard ball to another little billiard ball, and they were connected by a dowel stick. That's the way they draw it, right? Turns out that's not physical. Right? It's not quite like that. So how does a molecular bond work? And it turns out you need to understand the behavior of electrons. And specifically the behavior of electrons in the presence of nuclei, and how is very complicated. And it turns out that the way that quantum mechanics models this is something called Schrödinger's equation, which is this. And these are objects of multivariable calculus also. So this thing right here, for example, has a bunch of higher order partial derivatives in it, which is a multivariable calculus thing. And of course we see a there's a derivative there. And we're not going to get into the ugly particulars of Schrödinger's equation. It is beyond what we can reasonably do in this class. But when you get to that, among other things, you will be using multivariable calculus. Okay, so way I like to say it then, given that these are just a few very important, but nevertheless just a few of the applications of multivariable. Here's the nice little pithy summary answer to the question that I propose. Why are we studying multivariable calculus? It's because it's the calculus of the real world. So how's that for important, right? I mean, I think it's should be very persuasive. I mean, if you're going to live in the real world, which I think we are. Okay, pausing for questions. Anybody? Alrighty. Moving along. So, chapter 1. Good news. You've seen a lot of this stuff already. Different students have seen different amounts of it. But I think if you look through chapter 1, every student in the class will have seen at least some of it, and no student in the class will have seen all of it. So, everybody's kind of in the middle somewhere there. So I do want to remind you that linear algebra is a prerequisite for the course. Presumably y'all have all taken either Math 218 or Math 221, mostly 218 I assume. And make sure that you're good with all that stuff. Now, here's the good news. You don't need to worry in this class at all about non-diagonalizable matrices. It's not going to come up, not even a little bit, right? You don't need to remember eigenvalues or LU decomposition or all of that. The vast majority of the more, the trickier, the more sophisticated linear algebra stuff is not going to come up in this class. But some of it is. And so I'm going to go through a lot of chapter 1. I'm going to go through it fairly quickly, relatively quickly. Certainly the parts that are review for Math 218, I'm going to go through pretty quickly. And I should mention on that point, and I think I wrote about this on the web page, and I may have even said something about this in the recording, but I have the difficult task of picking and choosing what is worth saying in the very, very limited class time that I have to talk to y'all, right? I can't say it all. There's too much. It's not even close. So I have to make these tough choices, right? I would love to have about triple the amount of time that we actually have, and then I could say it all, right? Well, most of it anyway. But because I don't have triple the amount of time that we in fact have, I have to make these tough choices. And so, linear algebra, again, because you've seen it previously, I think the appropriate choice, rather than sacrifice, the time I need to spend talking about new topics that you've never seen before, I'd rather be tight with the topics that you have seen before. And there's these, pro-con, and, the optimization that I come up with is that we're going to go quickly through most of chapter 1. All right. Alrighty. So 1.6 is really very largely just a review of linear algebra. And so there's a couple of, so review of linear algebra material. That is most of this section. I believe you might, however, not have seen the triangle inequality. Maybe you have, maybe you haven't. It's an easy one to cover. Let's talk about this real quick. It's pretty believable. If you have two vectors and their sum, of course that's what this represents, then notice the sum, right? If you look at the magnitude of the sum, here, let me do it like this. If you look at that length of the sum, right? On the other hand, you could look at the length of the first vector and the length of the second vector. Hopefully, no surprise, the sum of those lengths, right? The dark blue path is, pretty clearly longer than the purple path, right? So triangle inequality is really pretty satisfying when you look at it just the right way. That the shortest distance between 2 points is a straight line. I think it's pretty believable. Everybody buy it? Okay. Boom. Okay. Here's one you may have seen before, but I think this is underappreciated. And this is I don't want to say a pet topic of mine. Anyway, I think this is underappreciated, and I want to make sure everybody's good with it. Now, I do know that everybody in this room knows how to multiply a matrix times a vector. What I am not 100% clear on is whether everybody knows all the different points of view that can be taken, and in some occasions need to be taken, on how to multiply a matrix times a vector. So in particular here, notice what I've got here is that the matrix vector product is a linear combination where the coefficients in the linear combination are the coordinates of the vector, right? And what is it a linear combination of? It's a linear combination of the columns of the matrix, right? So this is a nice point of view. A matrix vector product is a linear combination of the columns of the matrix with the coordinates of the vector as the coefficients. So again, you may have seen this already. If you haven't, then now you have. And if you have, then I want to underscore it and make sure everybody is comfortable with this. So the computationally more convenient formula in many cases is to do dot products, right? You take the row and you dot the vector, the column, row dot column, and all that business. And that has its moments. And if your goal is to just do arithmetic, then it's hard to beat that. I'd probably do it that way myself if I were faced with an arithmetic problem. The thing is, most of the time, we're not going to be faced with arithmetic problems. We're trying to relate ideas to other ideas, and from an ideas point of view, most of the time, the dot product point of view is not the winner. Most of the time, this is the better one for connecting ideas to each other. All exceptions granted, but very often, this is the essential point of view. Questions? Okay. All right. Okay, linearity. What is a linear transformation? And we're going to focus our attention, by the way, on what I like to call Euclidean linear transformations, namely linear transformations where the domain is flat Euclidean space Rn, and the target is Euclidean space Rm. Right? So I'm just going to abbreviate that by saying Euclidean linear transformations. So what we mean by linear is that the function satisfies this property. Right? This is what makes it a linear transformation. So why do we care about linear transformations? Well, that's a longer conversation. The short version is that they come up all the time. So they're extremely prevalent. They're fantastic tools, and they're ultimately very simple to identify and very simple to prove properties of, and it's just it's a win-win deal. They apply broadly, and they're easy to describe, and they're easy to understand. So that's why we care about them. They just come up all the time. Okay, so I know that you've heard the word linear a bazillion times in Math218. I want to make sure everybody is crisply clear on what it means, right? And so this linearity thing is an important thing to make sure that you're good with, and make sure you know the important, interpretations of linearity and that kind of thing. Okay, how we doing? Yep.
I have a quick question about Rn and the arrow to Rm.
Yeah.
Is that saying that then the function t normally occupies Rn space?
Okay, so great question. A lot of people. Let's see how to say this. I'm getting a little ahead of myself, but that's fine. So when you talk about a function is something that works between two spaces. It's not in a single space, right? So you have what we call the domain. That's where the inputs to the function come from. That's called a domain. And then the other space is the space where the outputs from the function go into. Right? So you can think of the function itself, and I'm going to call this function t, and you think of it, what it does is it takes stuff out of the green space and drops it down into the blue space. Does that make sense?
Yeah.
Yeah. Cool. Yeah. All right. Anybody else? Okay. Good stuff. Okay, so a couple of examples. And I think these first two certainly are relatively easy pitches. And I think that, by the way, it'd be a good exercise just to make sure that you're fully, brushed up on this, on a certain part of Math 218 anyway, to make sure that you can confirm for yourselves that these are linear transformations. Now, just a couple other things. The idea of this first one, let's look at this first example here. The idea is that this vector A is fixed. A is given. Right? And with A being fixed, let's ask, okay, what is this P function? What does P do? P is the function that says, whatever you come to me with, we're going to take a dot product with this fixed A vector. You give me an X, I'm going to drop X right down in there. I'm going to dot it with A. You give me some other X, I'm going to dot it with A. Right? So when we say P is linear, when we say P is linear, very often we will streamline the language on this and say that, well, I'll make a look. What is P doing? P is it's doing a dot product. So we will casually say dot products are linear. Right? It's a little bit of a sloppy bit of language, but it's common and it's convenient, and so be on the lookout for the what I call math slang, right? So casual, slightly sloppy, but nevertheless convenient and efficient language. Okay, all right. So likewise, cross products are linear, in the sense that if you fix a first vector A and use that to define a function, then that resulting function is a linear transformation. Okay, so good exercises to make sure that you can prove that those are linear. Now here's one that's a little bit more sophisticated, a little bit more counterintuitive, a little bit more confusing. Let's say that. So I'm defining this function D. Here, bad color choice. Let me... I'll use dark blue here. D, this thing here, I claim is linear. Now, wait a second. It says D is determinant, but is determinant linear? No. Determinant is not linear. If you take one matrix and add it to another matrix, determinant doesn't obey. It's not linear. Right? So very importantly, though, if you look at how this is written down, you need to distinguish between the function D that's being defined here and the function determinant that we're using here. So they are different. Determinant is a function that takes as its input an entire matrix. That is not what D is. So, by contrast, D is all of this. D does not take as its input an entire matrix. D takes as its input just a single vector. And now, how do I compute D? Given a single vector, well, I take that single vector and I put it down here in the bottom row, and keep in mind that these first several vectors were all given, right? So since all that gray stuff at the top was given, you give me one vector that completes my matrix, I can take a determinant, and bam, that's how you compute D. So D takes one vector in and then gives a number out. Determinant takes an entire matrix in and then gives a number out. So D and determinant are different as functions. Is everybody comfortable with that distinction? All right. Yeah.
So how do you prove linearity of a function?
Oh, yeah. So the way you prove linearity of a function in general is right here. You just prove that it satisfies this property. In other words, you'll compute this. Oh, why am I in gray? Let me get out of the... You'll compute this, and then you'll compute that, and you'll compute that, and then you'll add those, and then you'll ask, did this equation work? And if it does, for all values of a and b, and for all vectors v and w, then that's a linear transformation. And if it doesn't, for so much as a single case, if this equation fails ever, then that is not a linear transformation. Yeah. Okay. Yep.
So is it crucial that we're working with real numbers and complex numbers don't work, or is it just for simplicity that we're...
Just for simplicity, yeah. A lot of what we would do with linear algebra does, I mean, it gets a little squirrely in a few places. There are some strange aspects of, if you're doing linear algebra, what we call over the complex numbers. A couple of things get, dot products get weird. And so you got to be careful about that. As it turns out, we're not going to need any of that in this course, and so I'm not going to muddy the waters that are already plenty muddy with all of the other stuff we're doing with unnecessary complications. Yeah, totally. Great question. Anybody else? Yeah.
Just last thing about determinants.
Mm-hmm.
You're saying it's just not linear because it takes a whole matrix and...
Well, it's because it takes a whole matrix, and if you were to try to confirm the linearity, it would fail. And so, just here's an easy example. If I look at the determinant of 1001 plus 1001, that would need to equal to the determinant of 1001 plus the determinant of 1001, and this is just not true. Yeah, it doesn't work, right? So importantly, notice when I write this down, the inputs, what we're calling vectors in this case. I mean, they are vectors in the vector space of matrices that is the domain for this function. Right, and that being the case, this is one of the requirements of linearity, and it's just not true. Yeah.
So, can you have a linear function that takes a matrix as an input?
Sure, absolutely. Yep. Oh, yeah. No, this linearity does not require anything special about the well, it requires that the domain be a vector space.
Okay.
Yeah. But other than that, any vector space, absolutely. Right. All right. Moving along. So, this is one of the most important facts of linear algebra that y'all are going to need in this course. This is a very basic fact of linear algebra. I imagine this was probably covered really early in Math 218. I want to recognize that in Math 218, I mean, every instructor does things differently. Your instructor might not have emphasized this fact in the same way that I'm writing it here, might not have proved it with the same equations that I'm going to use to prove it here. But some form or another of this, I hope you will have seen at some point in early Math 218. So this is a statement about Euclidean linear transformations. And again, I want to keep it Euclidean just to avoid awkward issues that won't be relevant to us. And the amazing statement is that every linear transformation is a matrix. I mean, the pithy version of this is that every linear transformation is a matrix. To be a little bit more precise, every Euclidean linear transformation can be rewritten in this form where this thing here is a matrix. So, all right, but casually speaking, linear transformations are matrices. So really, really important fact. We're going to find it to be the case often that we'll have some function that is a linear transformation, and then we need to be able to say, it's a linear transformation, therefore there's a matrix that represents it in exactly this sense. In other words, just from the abstract property of it being a linear transformation, I can write down formulas. That's a foot in the door, right, algebraically. So, huge fact that we're going to use quite a bit in this class. So I want to talk about how to prove this part of it. Going the other direction is just a kind of a plug and chug, so I'm going to let y'all do that part. Let's talk about how to prove the down arrow portion of this. Let's assume we have a linear transformation, and not only am I going to show that it can be written in this form, but I'm also going to find an explicit formula for the matrix itself. Okay. All right, and so how to do that? Well, I'm just going to kind of start computing, and this is largely just a matter of writing it all down. If you have a vector, first observation is that vector is a linear combination of the standard basis vectors. Now let me interject. I know a lot of y'all either have maybe forgotten or have seen different notations, but the vector E1 is the vector that's all zeros except for a 1 in the first position. And then E2 is a vector that's all zeros except for a 1 in the I can talk faster than I can write, a 1 in the second position. Right? So y'all may know these more as IJK or something. Right? They're the unit vectors that point along the axes. Again, might be more familiar. Right? The thing is, if you use IJK, you run out of letters after. I guess you could do IJKL in 4 dimensions, but if you're going to do math in 73 dimensions, then you run out of letters, and it also just gets real silly, right? So I think it is much more sensible. As a matter of form, if we want to keep everything as general as possible, I like this E notation with the subscripts. It's very, very standard. And so if you haven't seen it before, no worries, here it is. But this is going to be my preferred notation for again, what you might have previously known as IJK. Is that cool with everybody? Okay, so with that in mind, it's a matter of just writing it down to confirm that when you know the coordinate, let's see here. When you know, bad color choice. When you know the coordinates of a vector, those coordinates are the coefficients in the necessary linear combination of the standard basis vectors. Very, very basic fact. I hope everybody has seen that before. If not, multiply it out. It works. Nice little convenient fact. Okay, we know we have a linear transformation. Linearity tells me this. Linear combination on the inside, linear combination on the outside. That's all. That's just straight up linearity. And now's where we make the insightful choice. And let me clean up my working space here. Get rid of that. The insightful choice is we're going to choose this right here. So specifically, I'm gonna the way I'm gonna create my matrix A is I'm gonna describe the matrix by way of its columns. Specifically, the columns are going to be given by these formulas. So said differently, A is going to be that formula right there. That's just an explicit formula. Now, before I move on as to why we care about this, let me say this a little bit differently. The way that this tends to get enunciated, and a fantastic little pithy memory tool is as follows. The columns are the images of the standard basis vectors. One of the most important insights, clever choices, however you want to say it, in basic linear algebra, is that when you have a linear transformation being represented by a matrix, the columns are the images of the standard basis vectors. Is that cool? All right, now, so what do we do with this? How does this help us? Well, quick reminder, we had already written down this. Right, so we were already here. And now, check it out. The columns are the images of the standard basis vectors. Okay, so AI is T of EI. I'll just plug those right on in there. And now I get this old familiar fact that we know from long ago, by which I mean on the previous page. And check it out. I've got a linear combination of the columns where the coordinates of the vector are the coefficients. This is the definition of A times X. And so we win, right? We have now shown that given this choice of a formula for A, the linear transformation can be computed with matrix multiplication. That's my matrix. So this is just ultra basic. This is, arguably the most important fact of linear algebra that we're going to use in this course. So please make sure that you're really, really comfortable with not only with this as a result, but with the arguments that go into giving us this result. Okay. All right, now, here's another fact of linear algebra, which we don't have time to go through the proof of. This is a little bit uglier, but also important just to make sure that you know, or that you remember, when you have two linear transformations. And notice this first linear transformation, I've written it as a matrix also, right? The matrix that represents S is this matrix A. So if I have two linear transformations, and if I want to talk about composing those linear transformations, so composing means that what comes out of the first one is then going to go into the second one. Right? Do y'all remember composition of functions? Let me write that down just to make sure. So here we're going to have T and then S in this order. So what comes out of T will then go into S. Said differently, this composition, written S composed T, is computed by S of T of X. When you compose two linear transformations, the matrix that represents it is the product of the two original matrices. So really important fact, not obvious. Really not obvious. I mean, I like composing stuff, and I like multiplying matrices, but it does not automatically mean that composition will just, of course, because it's convenient, work out to be the same as multiplying matrices. Thankfully, it's true, but it's not obvious. How we doing? So, really good news. All right. Okay, so by the way, real quick heads up, we just finished section 1.6. I know that's weird that we started with section 1.6. I just feel like it's got more prerequisite stuff than any other section of chapter 1, so I wanted to start with it and get that prerequisite stuff out of the way. And now we're going to pick up and start going from 1.1. By the way, there will be a few places in the course where I will kind of bounce around non-linearly between the different sections. Mostly I'm going to go in order, but there's a few places I'm going to bounce. Okay, so back to section 1.1. I got very little to say about this. It's vectors. Y'all should have seen practically all of this, if not all of it. Give it a read, of course, right? This is something I talked about in the recording, right? The intro recording is, everything in the book is fair game. And I have to make these tough choices about what to cover in class. I'm not going to have time to say it all. You're still responsible for everything that's in the book. Modulo the disclaimers in the content syllabus. Okay. Anyway, you're going to notice that this book and many others use bold to sort of accent a character as representing a vector. I think that's kind of a insensitive choice for a book to make because we as handwriters can't. Realistically, right? I mean, if you have you want to write CV, and you're going to multiply C times but V as a vector. So instead of putting the arrow over it, I guess I could sit here and I could, spend 3 seconds turning that bold. Nobody's going to do that. I think it's unfair to us handwriters. So much easier to put the little vector hat over it. That's what I'm going to be doing in this course. And not the bold. But heads up when you're reading the book likes to use the bold. All right. Future heads up for possibly more advanced math classes that you might take. In a lot of math classes, they do this. They don't put any sort of an accent or hat or nothing. They just say CV. And how do you know V is a vector? Well, because they said so 5 pages back, and you're supposed to remember. Right? So, okay, well, that's appropriate at higher level math classes. I still, to this day, find it very helpful and convenient just for kind of, in the same sense that punctuation is nice in a sentence. I like it just makes it easier to read, when I'm looking at an equation. I appreciate the convenience of the visual little reminder there. So anyway. Okay, here's another little quibble I have with the book notation, our book and many others. And so therefore you have to know this. Like to represent this vector as that notation. They'll say P1, P2 with an arrow over it. Now, here's the thing. You could just as well represent the exact same vector with P2 minus P1. Same. So why do I like this one and I don't like that one? I like the fact that the one that I've got here, it shows the actual algebra that's implicit to what's going on here. Right? So why is it that vector is P2 minus P1? Well, because I can think of P2 and P1 I could think of, for example, P2 as being a point, but I can also think of P2 as being a vector. And likewise, I can think of P1 as being a point, I suppose, but I can also think of it as being a vector. And the way you subtract vectors, right, is that is P2 minus P1. So, said differently, there is algebra intrinsic to this picture. Algebra is a good thing. When there is a good thing in play, I like to see it. Right? And so that's why I like this notation. So I can see the good news, that there is algebra there. Let's make our lives easier by making it visible. Now, this is just a notational preference. It's not a hugely critical point, but you're going to see me write this, and you'll never see me write that, other than to say that you'll never see me write that. Okay. All right. Okay, now, this next business... Oh, by the way, now we're done with section 1.1. So we're knocking out the sections. Let's see. By the way, let me check on the time. Let's see. It's 1:30. Okay, we're 12:30 to 1:45. Okay, so I have 16 minutes left. Okay. Section 1.2 has more stuff in it that's actually not from Math218. So I'm going to spend more time on section 1.2, parameterizations in particular, the first thing we're going to do here. I don't really think that comes up much in linear algebra, if at all. So we're going to spend some time on this. Okay, what is a parameterization? It's a very, very important concept, object. of study in this course. It's a function that gives position as a function of a single parameter. And by the way, we very often think of this as time. Not that you have to, but anyway. So position as a function of time would be a convenient way to think of what a parameterization is. But just to keep it general, just because we don't have to think of it in terms of time, let me say position as a function of a single parameter. Okay. All right. So here's an example. I've got position x comma y, and notice x is a function of time and y is a function of time, and therefore, since both of my coordinates are functions of time, that means that overall my position is a function of time, and that's what makes this a parameterization. Let's see here. Position as a function of a parameter. Everybody good? All right, so now in practice, let's suppose that these are those functions. So x is cosine t and y is sine t. That's an explicit parameterization now. So what does that look like? As position changes through time, what happens? What does this make? Right? And you can take a couple of different points of view on this. One thing you could do is just straight up draw. Here's, let's say there's x and there's y, right? And then you could say, all right, well, let's plug in t equals 0. I don't know, just to get started, right? Plug in t equals 0. That gives me 1, 0. That puts me here. Now what happens as t increases? Okay, well, as t increase, okay, well, this is going to be decreasing and this is going to be increasing, right? Flashbacks to calculus. So it's going to be, I don't know, kind of going that way or something. It's kind of hard to just look at those functions, at the coordinate functions individually, and really get a good picture of what's happening. However, neat observation you can make is x and y, being as they are these, all satisfy that equation. How about that? That's a slick move. Right now, where did I get that from? I pulled it out of thin air. I saw the equations cosine and sine, and it reminded me, hey, I know an equation that's always satisfied by cosine and sine, and therefore I know an equation that's always satisfied by my x and y here. Lucky break. Right? But what that tells me then is because all of these points satisfy this equation, and because that equation is something that I understand, it's a circle, right? That tells me that every point on this parameterized curve, well, they just move around that circle. They have to stay on this curve because they always satisfy the equation of that curve. Everybody see that? All right, so this traces out a circle. All right, and by the way, here's a related note. And so I wrote this down on in the text here. You can think of a parameterization as drawing the curve, right? So if you were to make a movie that represents position as a function of time, that movie would go like this. Well, at the start of the movie, it would be there, and then as time passes, as the movie progresses, you would just watch the point move around the curve there, and then continue, and just keep going more and more around the curve, over and over again. It's a really boring movie, but so the parameterization literally draws the curve. Does that make sense? All right. Okay, here's another one. This one's going to be a little bit less immediate, but what can I do with this parameterization? Notice it does give position as a function of time. I've got position, namely a couple of coordinates, both of which are functions of time. A parameter that I'm choosing for convenience to think of as time. Okay, there's a couple of ways that you can understand this parameterization. I first like to recognize, just as a reminder, don't forget the first coordinate formula there. I didn't explicitly write down that is x, but that's what a parameterization is. A parameterization gives position, and your first coordinate of position typically is what we call x, and your second coordinate of position typically we call y. Okay, with that in mind, a way to interpret what this is to step one, solve for that t in the first equation, plug that into the t in the second equation. All right, so solve for t, right? If x is equal to t minus 1, then t is equal to x plus 1. Take that formula for t, toss that into there, and then out comes, and don't forget, that second equation is just y. That's what y is. Y is 3t plus 4. And plugging in that formula for t gives you, you got to multiply it out and stuff, right? But that gives you 3x plus 7. So altogether then, let's just keep in mind that this here became y equals 3x plus 7. Said differently, this equation is satisfied by all the points on that parameterization. So line, right? High school algebra, so we know that's a line. So this is a parameterization of that line. Everybody good? Okay, so this move is a nice one where you take one of the t's, solve for it, and then use that to plug in for the other one. Nice move. All right, now here's a different approach you can take. It's just different. It's not better or worse. In different contexts, maybe one is better and the other is better in other contexts. But try to look for a relationship between the formula for x and the formula for y. Do I see any immediate obvious relationships between x and y there? I mean, kinda. They're both polynomials. They're both linear polynomials. That's a lot, in fact. They do have a lot in common. And so what I'm going to do is I'm going to think about what is the process. I'm going to try to engineer a process that would allow me to turn the formula for x into the formula for y. I'm just going to kind of play around. I'm just going to start fiddling with the formula for x until I turn it into the formula for y. And as I go along, I'm going to realize that, well, that's going to tell me literally how to turn x into y. So said differently, this process is the same as that process. And once I know how to an explicit process that turns x into y, that is an algebraic relationship between x and y. So it's just a different way to go about doing it. Here's the details. This formula that I start with. If I want to turn t minus 1 into 3t plus 4, there you go. Multiply it by 3 and then add 7. All right, that's how you turn the one expression into the other expression. Well, algebra, fair is fair. Do the same thing on the other side. Right? And the nice punchline then is I have a relationship now that y is equal to 3x plus 7. Everybody good? All right. So, why would you ever do the latter when you can do the former? Well, because look how in this case here it happened to be easy to solve for t. What if it's not? What if that expression for t is, what if the expression for x is a nasty equation and you just literally cannot solve for t? Well, then this path here is right out, right? But this might still work just fine. Okay. Here's a three-dimensional one. By the way, I want to point out sort of a big picture, stand back sort of perspective on, one of the things I'm doing here is the metaphor that I like, anyways. I'm giving you tools for your toolbox. There is no single way to understand a parameterization. Different parameterizations are susceptible to being understood by some tools and others by other tools, and it's just so you need to have a toolbox, and when you see some specific parameterization, you shuffle through your box of tools to find just that right tool that will help you solve that problem, right? But it's not just that there is a single way to do it. So this is just another tool for your toolbox. We've already got, I guess, 3 of them from the 3 previous examples. So let's talk about this thing. What is that? Actually, let me make a better color choice. What is this thing here? This curve. It's a parameterization. Position's a function of time. You'll notice that there are 3 coordinates, so we're in 3 dimensions now. That means we're looking at x, y, and z. Okay. First thing I want to do is notice all that good news right there. Cosine and sine. I remember that one. We talked about that on the last page. Cosine and sine. Oh, that makes a circle. Handy. So very often when you see familiar stuff in an example, you can use that to help you in your current example. Now, this old example back here was a 2-dimensional example. This is a 3-dimensional example. So how do I relate them? Well, notice where these cosine and sine show up is those are x and y. So what this is telling us is what the shadow looks like in the xy plane. If you ignore z, right, so we're just going to momentarily forget about that 3rd coordinate. If you just, in other words, project down into the xy plane, hey, you get a circle. All right, so I'm going to draw then right here. Oh, man. There we go. Okay, so this circle is, whatever the curve is, I don't know yet, but this circle is what the shadow of the curve is doing in the xy plane. Everybody good? All right. Okay, now, on the other hand, now let's project onto the z-axis. In other words, let's look just at the z-coordinate. Just z equals t. What does that look like? Well, that's t is just increasing at a constant rate. I mean, that's pretty easy to understand. Right? Z is, as time passes, z gets bigger. The bigger t is, the bigger z is. Right? So neither of these alone tells us what this parametric curve is, but if you put them together, it does. Right? And so all together then, I've got a curve, some sort of curve that as the shadow is doing this, it's also going up at a constant rate. Use your geometric intuition, and altogether that means that our curve is going around in a what we call a helix. Right, just geometrically, that's the curve whose shadow is the circle, go counterclockwise, and then whose z shadow is going up at a constant rate. Everybody happy? So again, tool for your toolbox. I mean, is every example going to be like this? No. Right? But some examples, you'll be able to capitalize on looking at projections in different ways and analogous to this. So just another tool that'll be useful sometimes. Okay. Alrighty. Okay. I'll tell you what I'm going to do. We're actually at a really good stopping point right now, so I'm going to go ahead and I'm going to draw the line right here. We're going to pick up here on tomorrow, and let's see, we're almost through with the 5th page. We're almost exactly on schedule. That's good. We'll pick up here tomorrow. Y'all have a good one. See you later. Don't forget office hours in my office starting at 2, which is in 15 minutes. And hope to see you there, or if not today, then some other future day. And see you tomorrow.